Hey! How are my friends doing today? Well, I know I did come in about 40 seconds after schedule, but hey, a lot of you and your friends are also not here as yet. Please get them online. What's up, everybody? Some of you might have seen me on the videos on YouTube. Some of you might have seen me on the videos on the app. Some of you might have attended sessions that I conduct with BYJU'S classes. I am perfectly audible. Awesome. Thank you. And I read some of those messages that came on before I came on. Guys, I feel so good. You have no idea. After a long day, this feels like the perfect set of messages that I had to open my eyes to when I'm kind of come here live for you guys. All right. Of course, we say live, but there's going to be about a 10-second delay. And if you like my teaching on the app, if you like my teaching in my classes, if you like the teaching that we do on YouTube and others, you got to realize this, all right? We have a truckload of people who are putting their heart and soul into it day in, day out, night in, night out to create the right kind of consumption for you, right? So it's not just me. You just know me as the face. I'm like the label that you put up on big boxes. But the stuff that's inside the boxes is so many of us. Today here in this studio, I have a technician who can help me sort of, go small, go big and all those pieces. And I have a subject matter expert who will correct me every now and then, and she's warned me saying, if you make one mistake, I'm like, I'm going to make a lot more than one mistakes. But then, luckily, I have her and I have you guys to correct course when I make a mistake, because this is what learning is, right? It's not about me coming and giving you, 3 glasses, yeah, thank you. It's not about me coming and giving you gyan. Gyan though, you'll get it anywhere. You have enough books, enough videos and all that. Why are we doing this YouTube series? You got full marks in science, that's awesome. I'm super excited about this session as well. This is awesome. Papia, I heard you, I see you. Like, I see you, but I kind of made a mental hearing. Hi. Awesome. Folks, we are here today. How was your term on exam, by the way? I hope everything went really well. It's a cakewalk. Come on, think about it. 8th, 9th and 10th standard. It was so long ago for me that I don't even remember feeling scared. I just feel really happy that I learned science and I learned maths so well that today I'm able to think about much better ways in which I can reach out to you guys through that basic science and math. It's sort of like the ground foundation for all the things that you are going to be accomplishing in the world going forward, all right? You are the future. That's it. Today, we're going to be starting out with term 2 content. I am here because I was really excited to meet a bunch of you. Science was super awesome. ICSE was tough. Oops. No worries. Tough is always a good thing. Tough just means that you're breaking through hurdles, right? I'm just here to sort of kickstart this series. Well, we are exploring atoms and molecules and ions, which is class 9 topics. If any of you out here are not from class 9, awesome. I love that you're trying to learn stuff that maybe is above what you are currently studying as it's prescribed to you. Or maybe you're coming back to recap a lot of these ideas. Also awesome, right? Because that's what I do every day. I keep revising. That's all my job profile is. That said, without further ado, and you guys might have realized this by now, if somebody doesn't stop me, I'll keep going on and on. Atoms, molecules, and ions, right? You've gone through this chapter in bonus. Video lectures are really cool. Thank you. I hope what we're covering in today is, hey, by the way, I'm not just going to be talking content to you, right? Some very theoretical pieces. I might brush through some interesting experiments and explorations. I might spend a little more time on, feel free to ask me questions. I might be delayed by a few seconds, but I'll try to address as much of that, okay? That said, what do these things have in common? And I'm just jumping right into it. What do these things have in common? You have a puppy dog, you have a tree, plants, you have a boy there sitting, seems pretty peaceful. You have a cactus out there. So please speak in Hindi. अरे यार कभी कभार ना जब मैं बात करता हूँ तो लोग मुझे बोल देते हैं कि भाई आप हिंदी में ट्राई ही मत करना. Speak in English because you're comfortable in that and you might do a better job. Atoms. Hindi, English, sir, all these are matter, right? Yes, all these are matter, they all matter. Camel, book, no matter what we can touch, feel, see, experience is matter. matter, material things that are made up of atoms. Now I do see that many of you, at least the ones who are participating on the chat, are people who know all of this already. So what really am I doing out here? Well, you know, it's beautiful that our schools and our curriculum is prescribing a few things that for us to cover. Most often people end up books, internet, teachers, classes, videos, all of these things, and people try to gather so much more of information. But trust me, it's about the process behind how we have come to this journey, how we have come so far in understanding matter around us. That is the fun part. Because if you understand that process, you can create miracles. Matter makes everything up around. Well, not really. Matter is everything around us. And it's made up of, like many of you said, atoms, molecules. Now, what exactly is this infinitesimally small pieces that make matter up? What exactly are atoms? What exactly are molecules? You might have some basic ideas. I will try to touch upon some of these ideas as well in this session and further sessions, and you'll have other teachers also coming and doing the same with you. All right, atoms. They are essentially thought of as the building blocks of matter, right? When I say they are the building blocks of matter, it took us a very, 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 very long time to be able to make this very simple statement so boldly. Who discovered atoms? I'm going to actually wait and see if some of you respond in chat. So screen is not clear. Refresh, get your internet connection. Matter, which have mass and volume. True, something that has mass and volume is something that you'd consider as matter. How existing matter is created? It's said that atoms cannot be created nor destroyed. Then how are they created? Beautiful question. Unfortunately, even I don't have the exact depth of scientific understanding to be able to answer this convincingly for you. But let's just say, now that everything exists, nothing can be created or destroyed. Whatever exists will exist. John Dalton, interesting, discovered atoms. I don't know about that exactly. But yes, he does feature in the storyline. Was it easy to discover atoms? Yeah, after all, I can just go look there, look at this pen, and then look closer, look closer, look closer, use a little bit of a magnifying glass, use a little bit of a telescope, microscope, and keep poking in, poking in, poking in. But there are limits, guys. There's so much of limitation that our technology to explore the world around that sometimes we'll have to resort to observations. Sometimes we'll have to resort to mathematical models. All those atom shapes that you would have seen, right? Let me try to draw some of those. Things like there's something here and there's something roaming around them and all that. All of these are not how atoms look. All of these are just some drawings and models of how we think they look. Democritus, Leucippus. Okay, interesting, interesting. Who coined the term atom? That said, let me say that I don't think any of these things can be attributed to one single person. It's been a journey of discovery. Acharya Kanad. Interesting, right? Let me start with a few philosophers from back in the day. I'm going to brush through this, and maybe a few scientists along the way as well, and then we'll see how the transition happened from a philosophical viewpoint to a scientific viewpoint. What's the difference, you say? This is about theorizing and coming up with ideas and coming up with explanations. This is about observing, verifying, making it such that multiple people can get that same or similar result repeatedly. That is the scientific process, all right? Way long ago, before Christ, or that's what BC stands for at least, Democritus kind of ended up philosophizing through his explorations and through his thought process that all matter is made up of infinitesimally small indestructible particles called atomos. Now, he didn't really go and say, I'm calling them atomos. Again, everything built up in the storylines. But his story of everything is made up of infinitesimally small pieces lasted for a very long time, all right? I might tell you 3 or 4 stories, but these happened over hundreds and hundreds and hundreds of years. You've got to keep that in mind, right? It's not like first standard you learn something and then third standard you learn something and fourth standard in this span of 1 or 2 years. Hundreds of years people were really trying hard to explore with the tools that they had at their disposal. Then Aristotle came in and said, hey, you know what? I'm being a little more critical than the previous person was, so I'm going to say that all matter is made up of either of these 4 elements: air, water, fire, or earth. Now, I don't know how each of you interprets this. I'm sure you've heard of this story, but air, water, fire, and earth. Some people say that these were attributes. Some people say that these were actual elements that got together in different ways. But in either of these, this was a very good philosophy, but it didn't really explain the real world around us. Then comes Antoine Lavoisier, who came in and said, I do not agree with Aristotle. Well, I don't really know how he would have spoken, I mean, his accent and all that. But anywho, he postulated that, he was doing a lot of scientific experiments. What are experiments? Different ways in which you can play around with matter around us and observe that maybe something causes changes. Maybe I could measure certain things, like I could see color, I could measure mass, so many beautiful things that I can do with technology and matter. He said that with all the probing that I've done, cheater, paduka kachayana, air is not an element but a mixture of different gases. Now, this is our interpretation of what Antoine Lavoisier might have said, right? Gases and how these different elements come together to form what we call air. Air in itself is not an element. Water is not an element, but a substance formed by the chemical combination of two elements. Now, of course, he did not really call it hydrogen the way we understand hydrogen and oxygen the way we understand oxygen nowadays. Back in the day, where there was some substance that he found would sort of react with this really prominent element and create water, generate hydrogen. That's kind of how he gave the name hydrogen as well. And oxygen, which was oxygen. I don't know if you've ever explored acids and bases. Oxygens are sour tasting substances, right? Something that generates oxygen or sour tasting substances, he called that oxygen, right? Fire, again, was not an element. Fire is a chemical reaction that gives off energy. You know, there's a funny question that we ask, is fire alive? I mean, something can be alive. Fire is not even a thing, right? Fire is a phenomenon that we give it a name called fire. Oxygen is involved in making fire, but oxygen is not fire. Burning is a process that we call fire, right? Atoms are particles that take place in chemical reactions and do not exist independently. I don't know about do not exist independently, because you know that there are some elements that exist independently as atoms as well, right? Speak clearly. I shall try. Hey, Antoine Lavoisier, like I said, he was probing a lot. He, through his probing, was able to identify that some property was there with how different chemicals combine to form other chemicals. And the kind of measurements that he was able to do is, he was able to measure how much of something was reacting to give a product. He was able to measure what was the mass of the things that were reacting and what was the mass of the products. And he was able to make some postulates. He was able to come up with these laws of chemical combination. Remember, he said that substances are made up of different kinds of elements, and those elements combine to give different kinds of substances. Law of conservation of mass, where, like one of you in the chat had already pointed out, matter can neither be created nor destroyed. Mass can neither be created nor destroyed, which means if I start out with a particular mass, no matter what I do to the stuff that has that mass, mass will still be the same after whatever I do, right? And somebody pointed that out, Proust's law. Of course, Antoine Lavoisier is credited to first having experimented with and observed this, validating it mathematically and validating it as a phenomenon, as a law, is something that's credited to Proust. But you can always say the law of constant proportions is something that also derives into the law of chemical combination. Now, these two are super critical, right? Not in that I want you to mug them up. 4 laws of combination, I'm assuming. Is that true or false? Now, there are multiple. As you progress further, you'll keep learning. Now, I like to say it this way, right? Sometime when you were a child, people told you the sun comes out in daytime and the moon comes out in nighttime. Is it true? Well, kind of true, given that at that age you can only observe so much, right? But now we know that the sun is not coming out or going down. It's because of rotation and how we are able to see it. And then someone told you sun rises in the east and sets in the west. Again, we know that east, west and all are nomenclature that we just gave to stuff, right? So as we keep observing differently and as we keep understanding the world around us differently, we start understanding laws and phenomena differently. Law of conservation of mass, law of constant proportions are not the all laws of chemical combination, but they are 2 prime ones that you need to think about. Now, here's an experiment that Antoine Lavoisier might have done, but I don't get intimidated. This is stuff that even I don't really connect with because I haven't done this experiment myself, right? But here's the broad idea. Looking at the setup, you can kind of guess that some stuff was taken here, something was done to it, and some product was brought out here, right? You can kind of guess that. I know it's written tin oxide and flask and heating apparatus and inverted bell-shaped container. Forget all of that. Some stuff, something happening to that stuff, and something being produced out of that, right? Simple stuff. Now, mass of the new substance is formed. He observed by actual mathematical physical measurement was equivalent to the mass of the stuff that was participating before the process was happening, right? This can be thought of in multiple ways now because we take it for granted. But remember, back when Antoine Lavoisier was doing this, he had to literally come up with own apparatuses to measure these kind of things. In fact, he created such a sensitive weight measuring instrument that it could measure really tiny things like even 1 milligram. And back then, they would really not have such precision instruments like we have right now, right? All right. Law of conservation of mass says that if it is a closed system, then nothing gets added in or nothing gets removed out in the form of matter or substances. What we started with, no matter what processes happen, is what we'll end up with. It might have different properties, it might have different features, but the mass is going to be the same before and after. Mass of products is equal to mass of reactants under law of conservation of mass. I want to change that a little bit, right? It's not under the law of conservation of mass, this is how it happens. This is how it happens, and we observe it and call it the law of conservation of mass. Great. Now, law of conservation of mass, if you had to write it down, basically says the mass can neither be created nor destroyed in a chemical reaction, right? I mean, if I say that this table has a particular mass, this water bottle has a particular mass, and I throw this out of this room and then I'll say, hey, mass of the table has reduced. Now I have to consider all of these things as a part of the system that I'm talking about, okay? So you've got to keep in mind, in that chemical reaction, under those closed constraints, as long as I don't add or subtract anything external to what I'm playing with, mass of reactants is equal to mass of products. Let's say there's an arbitrary chemical reaction. You know how that works, right? You write symbols on one side, which you call the LHS or left-hand side. You write an arrow mark, which says things are moving from reactants towards products, and then you have some stuff on the right-hand side. Let's say A plus B gives C plus D. In that context, mass of A plus mass of B is equivalent to mass of C plus mass of D. Now, why am I doing this again and again and again and again and again and again? Because I don't want you to mug this up. It's not about that one-line statement. It's about you understanding that no matter what happens when that arrow mark, whatever that arrow mark is indicating, the total mass on this side is going to be the same as the total mass on this side. If we were to take some examples, and I was trying to look for a lot of examples, and I found in a few of these books that you have this sodium sulfate reacting with barium chloride example. Now again, I don't want you to go into the chemical formulas of that right now, but just think about this. When sodium sulfate and barium chloride, look, everything is, it's stopped and there's, it's all closed container, right? When they are mixed together, or look at this, before they are mixed together, it so happens that the total mass out here is somewhere around 230.3 grams, okay? When we, what am I doing out there? Am I trying to pour it out? No, I'm not trying to pour it out. Look at the setup. You'll see that I'm intelligently trying to pour one of those substances into that other into the flask, all right? When I do that, the reaction that takes place forms sodium chloride and barium sulfate. Remember, sodium sulfate and barium chloride, now it forms sodium chloride and barium sulfate. And check that out, if I measure the weight again, it's still 230.30 grams. This is really cool. If I dig the earth and throw the mud away, will the earth's weight reduce by a few grams? Depends. What do you mean away? You mean outside of earth? Now are you going to say that the mud that you throw away is not a part of earth? Because what is earth if not for that mud? Philosophical questions again. Essentially, you get this, mass of reactants is equivalent to mass of products. Now, here's the interesting pieces of simple mathematics that you can draw to this, not just the philosophy pieces, right? Calcium carbonate. Now, don't worry. Some of you might quickly think about what is calcium carbonate, or some of you will be like, that is CaCO3. But does not matter at all. For now, we're just thinking about calcium carbonate on heating decomposes. What does decomposes mean? What? Calcium carbonate can rot like food and things? Not really. Decomposition is a particular thing that happens between chemical compounds. You will study all of these definitions and stuff in a lot more detailing and you'll get to understand that. For now, to form calcium oxide and carbon dioxide, remember I told you, we start somewhere. something happens, this is that arrow mark, and we end up somewhere, right? So reactants, something happens, products happens, right? Simple stuff. Cool. B, D, B, okay. I like it. I like it when they're not the same response from everybody. 5.6 grams, 5.6 grams, okay, super duper. Easy stuff, right? Sometimes you don't even have to think about the chemistry involved in this. You can just read the question, look at the numbers, and you'll be like, I know the answer. But how do we get that? Only because we are very confident that mass cannot change. Do you know that when 10 gram of calcium carbonate, or the reactant side, is decomposed completely, 4.4 grams of carbon dioxide, and if you know that, that's CO2, 4.4 grams is formed. What is the mass of calcium oxide formed? Only when we repeatedly observe that mass is conserved can we confidently say that this guy must be 10 minus 4.4 grams, which obviously, with all of you saying this, B triple infinity percent for sure. Infinity percent. Wow, I can't even imagine that in maths. Anywho, it's correct, right? 5.6 grams. And we can only say this for certain, even though I didn't sit down here and do the chemical reaction of calcium carbonate heating up and giving me calcium oxide and carbon dioxide, I'm still able to say this simply theoretically because I have repeatedly observed this over time again and again and again. Not I, humanity has observed this, and we derive a law in that manner, right? Understand this. It's not that I can do this because the law exists. It's that I have observed this time and again, because of which I formed a law to understand it. Okay, what is the type of reaction? Hey, if you kind of read the word out here, it actually said decomposes, right? So it's a decomposition reaction. If any of you didn't get that, it's completely fine. Not important for now, right? Cool. Laws of chemical combination, we saw mass. What is the other one? Constant proportions. Now, okay, here's the thing. The next set of artwork and assets that I'm going to bring up, right? It's going to give you some round stuff with some symbols and all of that. I know that most of you know what it is, but I want to point something out. Today, when I show you something like, let's say this is an H, this is an O, and there's one more H here. Can you guys tell me what this represents, the thing that I've scribbled up there? Can you tell me what that represents? Triangle over the arrow basically said on heating, okay? Awesome. I'm glad that you're focusing on and noticing those things, even when I said ignore it, because curiosity is the best. Water molecule, water molecule, water molecule. All of you know this because you're taking it for granted. For years together, you've been learning about these kind of symbols and these kind of representations. Back when Proust and Lavoisier were doing this kind of notations did not even exist. Alright, at least not in the way that we understand them today. So the kind of experiments and the detailing of observation that they went through, we can't even begin to understand. So you got to take a moment and think about how hard would it have been for those guys. I mean, if I gave you something and I said, I did not give you a ruler or a straight edge, I give you this pen and I asked you to measure its length, can you imagine how complicated that situation is going to be, right? You did not have the tools, is the state that they were in back then. Law of constant proportions basically tells us that in a chemical substance, any chemical substance, elements are always present in a definite proportion by mass. Now, if these are pure elements, they are present in 100% proportion, right? And what are those things which are not pure elements but are still in their almost indivisible form following molecules? Those are compounds, right? You've heard about that. Delta is heat, delta is heat. Yes, awesome. Doubt, what does a triangle? So, here's the thing, right? Candle. Now, if I bring a match out here and light it up, then flame comes, right? So I can actually say candle wick plus fire gives candle flame, right? Now to make all of this much lesser, much easier, I'm basically saying I have to heat the candle flame up sufficiently enough to get that candle flame. Candle wick to candle flame. That delta simply says I'm introducing heat. That's all it is. Okay, simple as that. Okay, back to this symbol. Here, this is something that you and I understand. But back in the day, he was able to still figure out that things exist as indestructible atoms. And those atoms combine in a particular way to give different properties. And in compounds which are not just made up of one kind of atoms, atoms of a particular element will still combine in a definite proportion by mass. Now you know that H2O is water. I'm not talking about 2 of H and 1 of O, not that. I'm talking about mass of the H inside water and mass of the oxygen inside water, okay? Cool. Now if I were to just extend this, ratio by mass of elements in water of H2O, what are the elements in water? This is basically hydrogen and oxygen. Mass of hydrogen to mass of oxygen. No matter where we pick water from, pick it up from your tap, pick it up from this water bottle, pick it up from anywhere else, pick it up from the rain that precipitates down and then cleans up. No matter what you do, this mass of hydrogen to mass of oxygen is always going to be 2/16 for water from anywhere. Now I see that a lot of people are typing 1:8, 1:8, 1:8. Why? A little bit of maths here, because proportions, ratios and proportions are generally expressed in their irreducible forms, right? So you will cancel that common factor out and you'll say it's 1:8, okay? No matter where you find it, even if you don't find it on Earth, even if you find it on like Titan, the Saturn's moon or any other planet and whatever, you will find it in this ratio. You cannot have water where hydrogen and oxygen have a different ratio of masses. Now, here are some simple stuff, okay? Like carbon monoxide, carbon dioxide. If any of you is watching this and you will be like, hey, but we said that elements combine in specific mass ratios, but look at this, carbon and oxygen is combining as 1:1 and carbon and oxygen is also combining as 1:2. How is that possible? Mind you, carbon and oxygen are the element constituents, right? It's like the leaves. What are the leaves that you make a salad with called? Lettuce, thank you. It's like those lettuce leaves and salt and cheese and all of that. That's the stuff that makes up your salad, right? But carbon and oxygen in themselves can also be substances, but carbon monoxide is a fundamentally different substance than carbon dioxide. Now what this law says is, no matter where I find carbon monoxide, no matter where I find carbon dioxide, जहां भी हो, जैसे भी हो, अगर मैं साफ कर सकता हूं दोनों को, carbon monoxide will always have carbon and oxygen in the ratio 3:4. Right? And carbon dioxide will always have carbon and oxygen in the ratio 3:8. This is like very important for you to understand. Abhi, aaj ke zamane mein we take it for granted, right? But back then, they really tried hard to come up and understand this. NH3, ammonia, will always, no matter where, have hydrogen and nitrogen in the mass ratio of 3:14. Remember mass ratio, because it's not H3N14 or whatever, right? That mass thing does not apply here. Don't get confused about those chemical symbols that you think you know and the properties that we're learning right now. They're slightly different. Alright. Sir, you speak Hindi? Yeah, I'm sure a lot of people will be surprised. Even if I watch this video later, I'll be surprised. Hey, I speak Hindi. I don't speak so well, which is why I'm not going to try too much. Anywho, now John Dalton, after all of these kind of experiments that a lot of these scientists were doing again and again and again and again, remember I told you we still haven't understood what an atom is. We know how elements work, we know how compounds are formed, all that is really cool. Parallelly, we were also trying to figure out what exactly is that indivisible thing that makes things up. And John Dalton had a proposition. I'm not saying that he is the best guy to solve for this, but he made a proposition. And a lot of other people also made that proposition. His became famous. He gave an appropriate explanation for the laws of chemical combination. You get that? We observed, we derived that this must be a law. Constant proportion, conservation of mass. Now Dalton was kind of able to explain these things. What does explaining something mean? Just giving deeper layers of understanding, right? You can always keep asking why. And at some point you'll get stopped. When your technology and your tools improve, you can go one deeper level further. So John Dalton gave one deeper level further explanation, built upon the idea that divisibility of matter. Remember, it was all such philosophical that matter can be made up of into particles which are, you keep dividing a pen, it becomes smaller particles of pen, and stuff like that. That logic. He named the smallest particle as atom, and he said that the interactions between these atoms can explain chemical combinations and chemical reactions, and that can in turn explain the laws that we observe. In other words, that's possibly how chemical reactions are actually taking place, right? Please solve some numerical on constant proportion law. Well, I did solve one numerical, but you know what I'll do? That was on conservation of mass. You know what, in some of the future sessions, right, me or maybe a few other teachers, we will do practice sessions which are just about the mathematics of chemistry as well, right? Hold on to your horses. For now, in the interest of, you know, exploring these ideas and the fact that it's almost half an hour in, I have a clock there, which is I was pointing there. I'm going to go a little further, but I hear you. Point taken, we will do some mathematics in chemistry, right? Awesome. Great. What all did Dalton say? Now, actually, we were talking just before the session saying, hey, can I introduce some cool visuals? Because in my head, I'm going, suddenly one matter will come and some magical animation will happen. It will go indivisible and all that. Yeah. Download the app. You'll get to see a lot more exciting things that we can do. But for now, I just want you to understand that Dalton did not just randomly sit up one day and say, hey, I think everything is made up of atoms. Atoms are indivisible particles. He went through a lot of grind and he observed repeatedly to understand and help us understand that matter is made up of tiny indivisible particles called atoms. And atoms could not just be created at random, right? Atoms had particular properties. They already existed. They could not be created or destroyed in a chemical reaction. I said this and I said this chemical reaction with such prominence because I'm sure some of you might be thinking, and I wouldn't be surprised if some of you put that on the chat also. So, but how do nuclear reactions happen? In that, you will have some electrons and protons and all popping out. That's not a chemical reaction, right? We are confining ourselves to the world of chemical reactions or chemistry, okay? Atoms can neither be created nor destroyed in a chemical reaction. And then he went on to say that the atoms of a given element are identical in size, mass and other properties. What does other properties means? The way they react with each other, the way they react with energy like light and forces and all of that. Atoms of different elements cannot have the same properties. They will have different properties in size, mass and whatever else, right? If the atoms are identical, they belong to the same substance. If the atoms are different, they have to belong to different substances. That's what we can infer from this logic, okay? Now you see, all of the things that we're talking about in terms of how elements, compounds, mixtures exist, in terms of laws that we kind of explored, all of this kind of start making sense at a little deeper level when we start thinking of atoms in this manner. I didn't get the second point. Atoms can neither be created nor destroyed in a chemical reaction. Very soon I'll tap into that, okay? Basically it says, if you remember that thing where the candle burning thing happened. Now the candle and whatever is burning and the gases that are getting created, it has some atoms, right? It's got some carbon, hydrogen, oxygen and all that. Those are just getting rearranged. No new atom is getting created. No existing atom is being destroyed. It's just kind of getting rearranged. That's all it means. It cannot be created or destroyed, but it can take different forms and it can group up with different friends. Alright, he went on to further say that atoms combine in simple whole number ratios to form compounds. Oh, now's when things connect, right? H2O. Now here, we're not talking about mass. This number here of 2 and 1, that's not about mass, right? That's number of atoms. Check this out. Dalton actually said that it's not just in mass, it's in number of atoms that they connect in those constant ratios. Now you see the correlations, right? Some correlations, some of you might be getting it. If you're not getting it, don't worry. As you further understand each of these, it'll work through. Ratio of mass in ammonia, ratio of masses in ammonia of nitrogen and hydrogen happens to be 3:14. But ratio of number of atoms of nitrogen and hydrogen in ammonia happens to be 1:3, right? Or 3:1. Think about it. You always have to be very careful about what keywords you're using because that indicates what you're observing and what you're concluding out of that, okay? Cool. In chemical reactions, and somebody who said I didn't understand point number 2. In chemical reactions, atoms are either combined or atoms are separated or atoms can get rearranged, right? For example, if I had yellow color clay and if I had blue color clay and I put them together and I mix them really well, what color clay am I going to get? Yellow, blue, mix. What am I going to get? I know, silly question, but give me the answer. No, chat, you're anyway typing stuff. Green. Thank you. Exactly. Now, if I had yellow color particles here and if I had blue color particles here, it's not that magically different new green color particles started getting created, right? It's still, if I poke down that green clay, I will still find little pieces of yellow color and blue color particles. New stuff has not been created, old stuff has not been destroyed. Things have just rearranged and start behaving different as a group, right? Cool, awesome. Hey, I answered the ammonia thing. If you didn't listen, don't worry. After this session, come back, play this video again. I have answered that question, okay? Is it true that mass will always be constant unless affected by chemical reactions? No. When affected by chemical reactions, mass will always be constant, right? It's not unless. Chemical reactions means mass will not get affected. Simple as that. Cool. Now we saw Dalton and everything is made up of atoms. Do you see how progressively we hit the reasoning? Why do things appear different from each other? Because the way the yellow guys were interacting with each other made the clay look yellow. The way the blue guys were interacting with each other made the clay look blue. The way the yellow and the blue are interacting with each other is making it look green. It's not the actual constituents alone that give the properties, but how they interact inside of matter, how they are combined, rearranged inside of that matter. That gives different properties. That's why they appear different. That's why they are different hardness, different shining, different color, different transparency, all that, right? Cool. Could you scroll up on the chat, please? Somebody said I didn't get something on Dalton. I just want to help understand that a little better. Okay, I think we're okay. Let's see. Cool. So if you want to come back to Dalton, don't worry, I might end up saying the same thing again and again. After this session's done, come back. This video is going to be there, hopefully, and you can come back to this segment somewhere around 36th minute or so, and you can figure this out, okay? Cool. Now that you understand all of what we've been exploring, yeah? Different substances are made up of different atoms. Now, I can't say that all atoms exist in all things, obviously, right? Some kinds of atoms get together to form, like atoms get together to form elements, unlike atoms get together to form compounds. When these guys are getting together, not chemically, but kind of physically, that they form mixtures. Hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Now here's one thing that I want to travel back about 35 minutes, right? Remember I told you, anything that you see on the screens here, anything that anybody can show you is usually just a model. Hydrogen does not look like a round gola blue color thing there, okay? Lithium does not look like one big round brown thing. These are just models to help you understand it, okay? Just to give you a visual. So next time you think about hydrogen coming from here and oxygen coming from here, you can imagine one blue ball and one red ball, right? These are just visuals to help you imagine and learn better, okay? What is the difference between physical reaction and chemical reaction? Awesome question, really good question. I want to answer this. So now here's the thing. There's some water inside this bottle, okay? You know the fun thing about green screens is if I keep it here, it'll be kind of like very weird looking. But if I keep it in front of my t-shirt, you can kind of see it proper. There's water inside this bottle. Now I'm pouring water into my body. Now the plastic of the bottle and the water of the water kind of physically existed in the same place here, right? Some of the physically existing water is no more there. That's kind of a physical interaction. But now this water that goes inside my body, you know that it's going to be promoting some chemical formulation. You know that it's going to be helping secrete some digestive juices. You know that the food that I ate is actually going to get digested and broken down and all that. Do you think that the way the food that we eat gets broken down is similar to this water getting separated from the plastic? Right? These guys are just physically next to each other. These guys are somehow chemically connected with one another. To understand this chemical connection is why we're exploring atoms, molecules and ions, right? How they behave, what kind of charges they have, what kind of bonding they might do and all that. That's exactly why we're exploring what we're exploring right now in the 9th grade that you're in. You're saying that the ration of mass, NCERT book 14:3 is written. Hey, lovely. Now I would like somebody to answer this, okay? Check this out. Can you scroll up? Somebody said, you're saying that the mass ratio is 3:14, but the book says the ratio is 14:3. Can somebody answer that question? I love this, and I'm not joking. I think this is a very relevant question, right? It's not mass of ammonia. Let me tell you this. I weigh about 75 kilograms, okay? I don't think that's exactly true. I'm just saying. I weigh 75 kilograms, okay? Somebody else weighs 50 kilograms. What is the ratio of our masses? 75 kilograms, 50 kilograms. What is the ratio of our masses? You might say 75:50. Or you might simplify stuff and say, you might say 3:2. But if somebody else says 2:3, is that wrong? I told you, right? Every time, 5-0, okay, not 1-5, Hema. Every time that a question is posed or a challenge is asked, you have to listen to the keywords, okay? You have to listen to keywords. I weigh 75, that friend weighs 50. The ratio of our masses is not a very good way to represent it. The ratio of Ashwin's mass to friend's mass is 75:50 or 3:2. The ratio of friend's mass to Ashwin's mass is 50:75 or 2:3, right? So it's not meaningful to say what is the ratio of masses in ammonia. Ratio of mass of hydrogen to nitrogen is 3:14. Ratio of mass of nitrogen to hydrogen is 14:3. You got to be very careful when you come about all of these things, right? Don't make silly mistakes or assumptions about, I've understood it, somebody's saying something. No. Probe into those keywords. Those keywords is where the detailing is, where the magic is. Okay? Cool. Means CO2 can be 1:8. CO2. CO2, you got to figure that out, okay? At 1 and 8 will not work well there. In H2O, 1 and 8 can work. In CO2, think about it, okay? Just think about it. Cool. Anywho, atoms are the building blocks of matter. Now, you know what these are, right? Elements. Pure substances. Are ions very reactive? We'll come to that. We'll come to that. I'm not going to take too much time. I'm actually probably not going to be exploring ions in this session too much. Maybe I will, or a few other teachers will explore ions with you a little further down, because we just want to make sure that you have a good experience. Okay. Vishnu, I love that question. All atoms are not circle in shape. We don't know the shape of an atom. I told you these are just models. This is not reality. This is just a way in which we are expressing reality so that we can imagine it. Okay. A pure substance made up of only one kind of atoms are called elements. Alright? Simple. Give me an example of an element. So, term 2 syllabus for class 10, term 2 syllabus for class 10 is the human body also made up of atoms. If yes, why? I don't know about why, but we can observe that, right? We have mass, we occupy space, we are made up of atoms. Okay, great. Carbon, cool. Hydrogen, nitrogen, iron, all of these things, right? Let's say I have iron nails, predominantly, not those fancy ones where there are alloys and stuff. You know what alloys are, they're mixtures. Iron nails, pure iron nails. If I go deep down inside, I will not have iron nail particles, right? I'm not going to have nail particles. Nail is just the way we call that. We're going to have the element iron. It's just going to be made up of iron particles and nothing else. Sometimes impurities might be there, but if I take a pure sample of iron nails, it's just going to have iron. I can't see anything else there. Ferrum. Thank you. Somebody said that. Somebody whose name is piano music said ferrum. Cool. I love that name. Yeah, I want to have some crazy guitar or something like that. Cool. Anyway, iron atoms is all I will find. I can't find anything else, because if I find anything else, then it's no more pure. Okay. What is quantum theory? I like that question. I'll come to that later. Anywho, you see, does anybody recognize what this thing displays? I don't expect you to know it. I'm not going to be asking questions about this. We're not going to be studying too much about this, but I'm just curious to understand. Does anybody understand what this representation kind of might be? Periodic table, nice one, Laksh. Okay, so I don't want to probe too deeply into that. I'm just happy that you know that word, but I really want you to study that and understand that deeply. We have, it says discovered, in some cases even invented, about 118 elements, and the quest doesn't stop there. We're still trying to explore more and more, okay? Now, all of these elements might have names to them, they might have some properties to them and so on. When I want to refer to elements with certain names and certain properties, valency, I like that. Valency is going to come up. I'm not going to do that right now, but it's going to come up in the next few sessions, okay? The reason I don't want to do that right now is I don't want to bombard everybody who's watching with all the information on the first session itself. I want to take it slow, not slow necessarily, but I want to really invest in understanding that it's not about facts, it's not about things that you can mug up, it's not about information, it's about appreciating those little subtle things like keywords, those little subtle things like where do you have to pay attention, those little subtle things like how do you get excited about somebody's journey knowing that he did not have the tools that you and I have, okay? Explain atomic mass. It is the mass of an atom. Okay, I know, you wanted deeper stuff. It'll happen. Hold your horses, it'll happen. Alright? Cool. Elements. It is quite inconvenient to every time call elements by their names, right? Now, I want you to realize this, okay? Some of you might know this, that carbon has an atomic number of 6. If you don't know atomic number, don't worry, you'll learn it. If you don't know what carbon is, don't worry, you'll figure it out. Some of you might realize that carbon has an atomic number of 6. And this is what I mean to say, right? We are taught that, we discuss that, we ask questions about that. But here's something that I want you to understand. Carbon does not have an atomic number of 6. We find that there is an element, and we repeatedly do some chemical experiments with it, nuclear experiments with it, and we see that, check this out, it's got some property which has 6 kind of positive charges and 6 kind of negative charges or something like that. It has some property which is number 6. Now, I see these properties, and then I start exploring other substances around, and I see the same properties repeating there, and I start exploring some more substances, and I see the same properties repeating there. Whenever I see the same property, I call that substance carbon, right? You have to understand that slightly, right? Carbon is not something that has an atomic number of 6 or an atomic mass of 12 or whatever. When something has an atomic number of 6 and when something has a mass of 12 or something like that, we call it carbon, right? All of these names and stuff are things that we give to observations that we make, okay? Now, we give names, but the number of times that we have to use those names when we are referring to chemistry, 8 to 12 friction and so on. Cool, reactivity series, awesome. How do we measure atomic mass, atomic number of mass? Atomic number of mass, that's a little tricky for me to understand, maybe a more relevant question eventually, and maybe we'll answer that. Great. So, we use symbols, right? Symbols are a shorthand way to represent things. Just like I told you, we use some models to represent scientific phenomena, even for some of those names, because you're going to be reusing it again and again and again and again and again. Just an example, right? There's one protein in our compound, usually a little under the skin. It has a scientific name, and it has a scientific name. If I actually try pronouncing that scientific name, it will take me about 3.5 hours or so just to pronounce the name of that one substance that's there, okay? So for simple reasons, I'll call it titin. If you're interested and you heard me saying this, you might want to go Google it or YouTube it or something. Just Google or YouTube scientific name of titin. You'll actually see people who have read that name, sit down for 3.5 hours and listen to that name, okay? But basically, I use one shorthand representation to represent that huge molecule, just like that. I'll use shorthand representations to represent anything that I want to refer to, okay? You get that? I kind of covered this before the acids came up, but I know you and I are on the same page on this. Now, multiple different kinds of people, multiple different societies, multiple different groups of scientists and scientific communities came up with different shorthand ways, okay? And some shorthand ways had good properties in that, you know, they represented elements and compounds and mixtures really well. Some shorthand ways represented certain properties, but not all properties. But in the world of communication, we want something that everybody can understand, and it kind of covers a broad spectrum of ideas, right? So then we came down to something called the Berzelius System of writing these shorthands or writing these symbols. In this, the symbols of elements are made from 1 or 2 letters of the name of the element, right? I think I said name of the elephant. I meant name of the element, okay? Cool. I'm not going to go too deeply into this. You kind of already understand this. Either the name of the element in English or name of the element in Latin nomenclature. Hydrogen, H, the first letter is the symbol. Fluorine, F, the first letter is the symbol. Helium, first letter is not the symbol, because first letter would be H and that would be hydrogen. Oh, so we took 2 letters, right? You see, there's some nice workarounds and you can actually figure all of these things out. Lithium, Li. Manganese, Ma. Oh, why are we doing Man and not Mn and not Ma for manganese? I'm going to probe these questions to you. Let's see if you can figure them out. But there are some very nice ways you can understand this. You don't have to mug them up. The more you repeatedly use all of these, right, you'll try to understand, you'll understand all of this really well. Greek as well. You're right. Cool. Now, Latin and Greek. See, I missed it, but you caught it. I told you right in the beginning only. I have some friends here and I have some friends there also who are helping me get on the same course so that we explore it together. Latin and Greek names, again, first letter or 2 letters or 2 most prominent letters. Okay, super duper. Now, some of these atomic symbols, now you might think that you want to mug them up. What is a nuclide symbol? I'm not really sure, Vishal. maybe you'll have to ask me a more detailed question and maybe I'll be able to give you an answer. But I'm not really sure what a nuclide symbol is. I'm so sorry. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and sodium. These are the ones that are listed down here. Okay, cool. I don't want to explore too much more. It's already been about 15 minutes into the session. What do you guys think? You just want to spend 2-3 more minutes just so that we can talk about things and I can understand what really you want. I can see that you want to understand reactivity series. I can see that you want to learn about valency, you want to learn about charges, you want to learn about ions. That's awesome. I really want to explore all of these things, and a lot of us teachers and a lot of us content creators really want to explore this with you, and we'll keep doing that, all right? What forces binds things inside atoms, what forces bind atoms together, all that will happen, okay? Reactivity series and all that. Cool. I'm not going to explore that now, but over time we'll do that, okay? For sure. For now, I just want to say atoms of most elements do not exist independently, right? Some elemental atoms do exist independently, and you might have heard of them as noble gases like helium and argon and all. But most atoms are reactive. They have a property by which they want to react. And if I want to understand that, what is that property by which they react, I will end up understanding chemical reactions. I will end up understanding what are those bonds and forces that cause bonding and all that, right? That's exactly what exploring chemistry is, okay? That's a really cool thing. Just to explore something, you will open a world of science in front of you. Oxygen generally combines chemically with another oxygen atom and exists in a state where two oxygen atoms are sort of combined together. What do you call it? Supercalifragilisticexpialidocious session. Cool. Thank you. I'm just hoping that that's a compliment and that's not a you're not scolding me. I know that word. I also know pneumono-ultramicroscopic. That's yeah. We can share some stuff later eventually. Anywho, you see that when we say atom, it is so tiny that a group of them is what we experience as matter around us, right? We really need instruments and tools to be able to probe things down at the atom level or the molecule level and so on. Molecules, exactly, right? So atoms combine chemically to form molecules. Now, substances are also formed without molecules. This is where ions come in, okay? These are called formula units. You'll explore that in a little while, okay? Cool. I hope you realize from our earlier explorations to Dalton, to all the things that we've explored about the laws and those little discussions that we've had and what to look at, what not to look at, and the fact that a red ball, green ball and blue ball is not how atoms look. This is just models for me to kind of talk to you, to say that atoms can be of the same or different kinds. When you have same kinds of stuff, it's pure and we call that an element. When you have different kinds of stuff, we call it impure, and if they are chemically bonded together, they form molecules of compounds, okay? Cool. Now, you gotta understand some basic examples. You might have to mug a few of them up, but trust me, the more you read and the more you keep doing stuff, you will pick it up automatically. It's like, you know, sometime you had to really sit down and mug A, B, C, D, but the more you do it, it kind of becomes second nature, right? Now you really don't have to think about what are the alphabet of the English language, for example, or what is E, E, U, U, whatever else, right? Whichever language you want to think about. Nitrogen gas, oxygen, ooh, that's not oxygen. What is that? That's O3, ozone. Oxygen can also exist as 2 atoms and 3 atoms. Now, it looks like I'm exaggerating and making some fake emotions and all, right? But do you see that beautiful, beautiful chemistry behind how is it that 2 atoms can exist and how is it the same stuff can be 3 atoms? Guys, I really want you to explore this. I hope you have a beautiful journey exploring all of this, right? Essentially, molecules of elements have some properties that we can explore, but I think I will stop at this point just to help us realize that we can keep going on and on and on and on, but at some point we have to understand that it's not just about information. We'll have to plan the way we explore science. We have to actually practice what we explore. We have to observe and we have to make stuff. We can't breathe O3, ozone. Oh yeah, I had done one YouTube video also, no, about the ozone layer. I hope you guys see that. I mean, not just me, we have like a truckload of teachers who are doing some really beautiful videos. I'm not just saying beautiful videos, I mean, we're spending a lot of time into understanding the concepts behind it and how we should actually animate it, train people to understand and represent that so that you guys can understand that really easy. And that's going to be our endeavor through the 8th, 9th and 10th channel on YouTube. That's going to be our endeavor through the apps that we do. That's going to be our endeavor through the sessions and classes that we do. We're really here at the end of the day just to be able to give you better avenues to learn things and get you excited and get you curious, and hope that you keep exploring whatever you choose to learn, right? We're going to be coming back to you every day with content for your term 2. We're going to be coming back with exam related stuff, non-exam related stuff, deep dive into concepts, deep dive into practice, doubt solving, live interactions. All of these things are going to keep happening, okay? Somebody said, Suman said titin is an element. No, titin is not an element, it's the name of a protein, okay? Cool. Are we good to close the session, folks? Can I hear it from you guys? Are we good to close the session? I hope you have a wonderful evening ahead of you. And I really enjoyed this. Thank you for being so interactive and helping me say the things that I want to say and helping me learn new things as well along with you. And until next time, and we'll come back to you every week. Please make sure that you're subscribed into the channel. I'm not saying this just as a marketing gimmick, but unless you are subscribed, I will not be able to reach out to you. And unless I'm reaching out to you, I'm not really doing my job here, right? Because my job here is to teach, not just to record videos. A student makes the teacher in a very funny way. Great. Thank you. How do we do the exit? Do you want me to like vanish away, or I'll just say bye-bye and I'll drop?